Hello, hello, this is Greg Wagner with the, I believe, sixth in our series on going over the constant satisfaction problems. So constraint satisfaction problems. Hello, this is Greg Wagner going over Hello, this is Greg Wagner for CSCV 471, Introduction to Artificial Intelligence at the University of Arizona, going over constraint satisfaction problems. So if you go back to lesson 1, we went over the 8 queens example. Basically what you try to do is get 8 queens on the board without any of them being able to capture each other. And you can do this by purely generating test, which on an 8x8 board is not that big of a deal. You could basically calculate that in a few seconds. But if you get to a larger board, like you will have to do for this n queens assignment, it could be computationally very intensive. And so you could do basically a generating test or brute force, basically just trying all the different positions. But we want to do a little bit smarter algorithm, so we're going to use constraint constraint satisfaction solutions to solve this problem. Now, while the examples we give are somewhat trivial, these solutions are also used a lot in scientific computing as for optimization, which basically tries to figure out what an equation is or where the best place to put different variables are, given only constraints and certain factors. So for the 8 queens, you have 8x8 board, and so kind of the test and generate would be you just randomly place the first one, and then the black pips represent the places you can't put them. So we can't basically put a spot in this row. Basically, you would go from left to right and just basically randomly pick spots until you get it. And so this one, we have the spot here, which is good. Now we're going to break this one out, and so we limit the spots. And so if we go here, more and more spots. And so what we need to do to actually make this more tractable is not just use the successor function and a goal test, but also mean to propagate the constraints imposed. And so instead of just having successor functions, as each step goes, you add constraints. This is very similar to the game problems we had, except it's not adversarial, looking for the worst case. It's basically saying, okay, how can I do this without it still going forward? And so basically what you're going to do is you're going to have explicit representation of the constraints and constraint manipulations as you go forward. And we'll go back later, but basically you kind of try to plan ahead a little bit, knowing where the constraints are going to go to help you out. So for the constraint satisfaction problem, we'll also call this CSP for the rest of it. You have your set of variables, and then each variable x to the xi has a domain of di of possible values. So it has to basically, you have a values and then where you can possibly put it. And then usually the d variable is discrete and finite, and then you also have a set of constraints. And so each constraint, C of k, involves a subset of variables and specifies the allowable combinations of values of these variables. So basically, your set of constraints will say, okay, I have this going on. What ones are limited to now? So if you think about this, as your constraints become, you're going to start to get more and more constraints less and less allowable positions as you add more variables, set more variable values. And so for the CSP values, we have what I defined above, and then you basically have to assign a value at every value to every variable so that all the constraints are satisfied. So the goal is to get all the constraints satisfied. And then for the 8 queens problem, you have 64 variables. Those are the different spots you're going to do it. The domain for those variables is either 1 or 0, so there's something on it or not. And the constraints are, for xi1, xik is equal to 0 for all k1s, and then for ij1 equals xk0 for all the k's going 1. So this is basically saying you have constraint for the columns, I is the columns, and they have constraint for the rows, or k are the rows. And then also you have something similar for the diagonals. It's just a little bit harder to implement. And then your values are going to sum as xki are going to equal to 8. So there are 8 variables, x of I is 1 to 8. The domain is each variable from 1 to 8. The constraints are in the forms of basically you can't have multiple values on both columns and rows. And another example of this problem would be the color mapping problem. There's a theory, it's called the 4-color theory, that you can draw a map only using 4 colors. This has not been proven mathematically, but it has been proven empirically. And so I had a math professor in college that basically said, well, it has been proved empirically for like these huge sets, but I don't consider it actual proof unless it's proved with a closed form, which means that there's a formula to do it. But he's like, well, but it kind of makes sense, but I'm a mathematician and I need a full proof. And so, but for the map coloring, basically what we want to do is use as few colors as possible. So in this case, we have 1, 2, 3, 4, 5, 7 territories, and we want to use as few colors as possible. And so the variables for this one are the different territories: WA, NT, SA, Q, NSW, V, and T. And each variable has the same has the same domain. The color is red, green, and blue. And then no two adjacent, and the constraints are no two adjacent have the same value. So this is basically all the permutations of the different values that can have them. And then we color them in. So basically what we do is start with red one and then see which ones we can't do with that one and then move forward. And then if there's a finite number of domain values, we have a finite CSP. And then we can also have infinite domains. Usually it doesn't happen, but we have infinite CSPs. In this case, we only consider finite CSPs. And so for the binary constraints, you can see these are their connections, and basically you can't have the same values for each one of these. So notice here T is an island, so it doesn't have any constraints. Basically you can put whatever color you want on it. But all these other ones have different constraints applied to them. And then so you can do a graph where we have territory 1 is related to territory 3, territory 2 is related to territory 3, and territory 4 is constrained only to territory 1. And then so if 2 variables are adjacent or neighbors, if they're connected by an edge or an arc. And then so if we define CSP as a search problem, we have our basic steps. We have our initial state, we have an empty assignment, we have a successor function, a value is assigned of any unassigned variable which does not conflict with the currently assigned variables, a goal test, the assignment is complete, and the cost path, there's no cost in this. So basically we have a problem, but we make this into a search problem, we can apply algorithms. And then with n variables at domain size d, the big O of this is going to be d to the n, distinct complete assignments. And so it has, again, a lot of these problems have exponential growth, but we want to try to limit those. And then this kind of just goes over the finite CSP include a 3-stat as a special case. 3-stat is known to be NP complete, so in the worst case we can expect to solve a finite CSP in less than exponential time. So basically this is saying is we really can't. Best performance, the worst case performance is exponential time, essentially the big O and the big little o. Commutativity of CSP, the order of which, so for CSP, the order of the values assigned doesn't really matter. So I showed in the 8 queen thing, we start from left to right, but the order doesn't really matter. And so you just generate successors of the node by considering assignments for only one variable. So you basically have the variable at the time. You don't need to consider too many steps forward. And you don't actually have to store the path to a node because it's part of the constraints, and also you don't have to consider, you can start pretty much anywhere you want. And so one of the CSP algorithms we could use for a search is the backtracking search. So we have an empty assignment, so our assignment value in this case is an empty set, and then we have our variable 1 is going to be this leftmost, which is going to be v11. And so the next assignment is going to be V21. So it's this one here. This one is going to be V22. And then we have V31. And so now we hit the node. We're going to backtrack, and then we just ignore that. We said, okay, this is not the path we're going to go. And then now we jump back, and then we ignore this one. So we're basically, when we jump back, we're only doing the assignments for the ones, basically if we're at a certain variable, we don't have to redo the paths. So we have 3, and then again, this is V31, so this is basically ignores this whole entire path, and this is 3.1 and 3.2 as well. This one would be 3.1 and 3.2 as well. And so for the backtracking algorithm, we initialize with a empty set, and then we have our assignment set. And if A is complete, then return to A. So basically, if we've done everything in A, you assign to X, select an unassigned value, and then for your X variable, and for your domain, select an ordering for the domain of X. And then for each value, V in D, so each of the D values, you do this loop. And if V is consistent with A, then you add V to the X space, and then results, and then you call what's in your space, then you do the backtracking again. And if the result is not a failure, then you return the result. And so you keep on doing this loop until you get through it, and then you return if there's a failure. And so for the coloring algorithm, the way this would work is you have your first spot, WA, is going to be red. And then you do WA red, and then you're going to put a green one here. And you do WA green, red, and then you can see here we have this path is Q. We can put blue there. But notice how, since we have the constraints there, we're not going to do, this left column is always going to be kind of red, green, red. Notice how we're not going to put SA as the next case. And so kind of the questions for you are, and I'll take a little stop, is which variable X should be assigned to the next value? In which order should its domain be sorted? And what are the implications of partial assignment of yet assigned variables? And so to answer the partial assignment variables is you're going to, that's what the backtracking solves. So the backtracking is what are the implications of partially assigned variables? That's where you're going to do the backtracking to make sure that all the variables have an assigned value. So for the color mapping, we have red, green. So we know that we can't use red for the next one on the path. And so we're going to try to do blue because we have red, green, blue. And then for the next one, and then for the queen, where are we going to go next? We're going to go from left to right. So we go here, here, here. We're going to go here. So what is the implications as far as pipping? All of these, this row is going to have the black pips, and then this diagonal will here. And then so you need to update the constraints as you move forward. And then we have also another here, how you choose the variable, use a minimum remaining value heuristic, or MRV heuristic. It's called the most constrained variable or the fail first heuristic. And you basically, you want to fill out a variable with the fewest remaining values first, so you can get that assigned and then move forward. So in this case, SA is going to be the MRV because it has so many things on its edge. So you have the most edges from it. What would be the opposite? What would be the least restrained variable? It would be T because there's really no restraints on it. So this one has the most constraints on it, and this is the one you would maybe want to start with. And like I said before, select the variable that has involved the largest number of constraints on other unassigned values. So for the choice of the value, in this case, we have SA at this point has no options because it's being touched by all the different colors. So better would be is to make this one, one color and then change all the other ones around it. So instead, if we change this color, this one becomes blue, and now this becomes a valuable option. And so the least constrained value heuristic is prefer a value that leaves the largest number of subsets of legal values and unused variables. So for local use of CSP, we started with our initial values, and then notice here how these two cannot be next to each other. And so we're going to try to clean this up. So we're going to do this one constraint. So this one is constrains with 1. This one interferes with 2. So we have row 3 here. I mean, sorry, this place has the most number of constraints. So we do this one. We have this one here. And this last space has basically 2 constraints for all the space except for here. And so we'd want to move this one to this space here. Now look at this one. Which ones are in conflict with each other? In this case, none of them are. And so that's why we move this space to here. So we have this one. So let me back up. So in this space, we have the least number of constraints on this one. So we move this one up here. And then now, this one has the least number of constraints. However, this spot opens up. And so to pick initial complete assignment at random, and then pick a conflicted variable at random, and then select a new variable, var, to minimize the number of conflicts. If the new assignment is not conflicting, then return it. So basically what it's saying is, you kind of initially assign the values, and then try to pick the one with the least number of constraints, and then move those around until you get to the right spot. And this is called a minimize conflicts heuristic. And so local search with a min conflict heuristic works extremely well for million queen problems. The reason solutions are not densely distributed in the M&N space, which means are densely distributed in the M&N space, which means on average the solution is a few steps away from at randomly picked assignment. So basically saying is randomly put the values out there, they kind of fix the ones as they go along. And so we've answered the first 2 questions. Now how will we answer the third one? So for constraint propagation is a process of determining how the possible values of one variable affect the possible values of other variables. And so we do is called forward checking. So after variable x is assigned at value v, look at each unassigned variable y that's connected to x by a constraint, and then delete from y's domain any value that's consistent. So basically it's saying, I'm going to put down x, and I'm going to basically see which domains for like this row, this row, this row, this row are not available to it. So for the color mapping, for WAP, we have RGB, so we all the constraints to it. So I'm going to assign R to red, and so now since R is connected to N and T, G and B are not available. R is not available for this one, nor is it available for SA. Now I'm going to add B and G for NT and Q. So that means SA only has B available, as well as NST now doesn't have green available, but since Q is attached to NSW. And so now, when I make VB, SA has no valuable options. And so it's impossible assignment that forward checking does not detect. So basically it'll say, okay, you cannot detect that these are eventually going to be in conflict with each other. So maybe this value should have been green and this one should have been blue. And so you basically have to say, okay, when I have no more options, maybe I should start changing the values, and that's what this is basically saying. And there's some other ways to constraint propagation. We can do Are Consistency. And so notice here how T has RG and B all the way through. And so we have this Are Consistency. And so basically you want to say remove Are Inconsistencies returns true if and only if you remove a value. And so if value is removed, you're going to put this in the J in the set and move through these values. And so basically what this is saying is if the R stays the same if there's no basic connections between it, for every value you're going to just kind of basically check for it. So to kind of go further through this, for every value of x in x, if there exists no value in y such that value that y, x, y satisfy a constraint, j and k, then remove x from y. This is empty, and then if x is empty, then there's a contradiction, and then remove y. So basically what this is doing, what the Are Inconsistencies is doing, is basically just checking forward if there's any way that things are changing. And from the general constraint problem for binary constraints is for algorithm, it's called AC3. If you have a contradiction, you start off with contradiction equals false, and then you have a stack of all arcs, basically all constraints of CSP into Q. So while Q is not empty and not a contradiction, do this. You pop Q into JK, so those are the two different constraints, and then remove any arc inconsistencies with that. And then if there's a contradiction, return false. And then you basically would try it again. And for every variable MK, do except JK except do, and then you would add to the stack. And so for this algorithm, complexity is essentially quadratic. We have n as the number of variables, s as the maximum number of constraints, and the d is the number of variables. And basically d is going to be your limiting factor. And so if you look at map coloring, we have this area packed here where we would maybe say, okay, Washington or WA and NSW can both, since they're not in the same arc consistency, these can have different values. These can have the same values, and then assign those values, and then move, and then you can see these constraints down here. And then I say, is AC3 all we need? And no, because you may have a case where you have three linked things and you can't all share the values. So to solve a CSP, you can interweave constraint propagation using forward checking or AC3 and backtracking, and then take advantage of the CSP structure. So basically takes advantage of the different arcs you have on your graph. And so for the revised backtracking algorithm, to kind of solve the last problem, is you have an empty set. If A is complete, then return A. And then if an unselected variable, put it into X, and then select an order in the domain for X. And for each value V of D, if V is consistent with A, then add A to X, apply the inferences, and then inference does not fail, add our inference D. Then do backtracking, and if the result is not failure, then return the result. And remove remove V from X and the inferences from it, and then return a failure from inferences from A. And so for the to kind of show how it is for the four queens problem, let's kind of walk through this algorithm. So we're going to start with X1. We're basically just going to put it in the first spot in it. Sometimes you can just see it randomly pick spots to kind of make it look a little bit more interesting. And then so now we're going to go to X2. And then so notice here we're eliminating the domains for all the other ones after this. And then if you're using AC3, X2 leaves no room for X3. Basically the reason why that is if you notice X4 also has X3 in it as well, has 3 in it as well. So basically it's going to say, okay, now I'm going to put this one in 4. And then if you propagate that forward, as a result, AC3, X3 has no room for X4, and X3 has no room for X2. So we're going to go again, I'm going to try it again. So we eliminated, so basically it's saying, okay, I'm going to look forward and see if it has this, and basically gets rid of all the options. Then for the next one, so I'm going to try row 2. And this basically is going to eliminate 4, 2, 3, and 1, 2, and 3 for 4. So you're going to remove 3 for this one because you see in the last one, 1, 3, and 4 has options there. So we basically say, okay, I'm going to remove 3 just so 4 has more options. And now it basically eliminates 4 from, then you propagate again, you see 2 only can have 4, so that eliminates the option 4 from 3. And so we can place all the spaces there fairly quickly. And so if the constraint graph contains multiple components, then one independent CSP per component. So basically it's saying if you have multiple constraints, there's at least one kind of constraint that you can fit for all of them. So the constraint graph is a tree, no loop, and CSP can be solved efficiently. So for a constraint tree, we have X, Y, Z, U, and V. And you order the variables from the root to the leaves. So in this case, you order the values as U, V, Z, U, V. So you're basically going from the root, going to left, you're going to do Y, going to go, so we're doing a breadth first search, S, U, V, W. And then order the variables in the root from the leaves, and then for J, N to N minus 2 to 2, N minus 1 to 2, remove the Are Inconsistencies where Yx is the parent of Y2, assign the legal value to Y, and then for J to 2, assign the values consistent with the parents. So to kind of show how this would work, you start with SA, and you basically remove it, and then make a tree out of it. So whenever a variable is assigned by a value of backtracking algorithm, propagate this value, remove the variable from the constraint graph. So basically, pick the one that's the hardest one to do, and then keep on removing them as you use them. For non-binary constraints, so far all constraints have really been a binary, so 2 variables are unary, 1 variable. Constraints with 2 more variables can be difficult to propagate. And so theoretically, one can reduce a constraint to k greater than 2 variables to a set of binary constraints by introducing additional variables. So basically, if you have some kind of intermediate ones, you can kind of do some additional variables. And so when do you use the CSP techniques? When the problem can be expressed as a set of variables with constraints on their values. So basically you have some kind of constraints on them. If the values go from infinity to infinity, you can't do this. When the constraints are relatively simple, so either probably they're binary, so kind of like a tree search. And when the constraints propagate well. Basically means you can kind of pass them forward, and then when the solutions are densely distributed in the space of possible assignments. So you basically have a certain space where you can assign the values. So the main one, actually the main factor is this first one, where the problem can express a set of variables with constraints. Hence the name, if you have constraints for the CSP, the C, this problem can be solvable. And so CSP techniques are used to solve very complex problems. They're usually used when you have like finite resources, so crew assignments to flights, animation of transportation fleets, flight and rail schedules, task scheduling and port operations. Use them for design. You're kind of used for brain surgery. You'll say if this happens and this happens, you're gonna have problems. And as far as design goes, basically you have these different. Basically, when you have allocation of resources, so there's a finite thing. This is also used sometimes in kind of microeconomic theory. So we went over constraint satisfaction problems. The CSP is a search, basically it's a search problem. We went over the backtracking algorithm, the general heuristics, local search techniques, forward checking, constraint propagation using AC3, interweaving constraint problems, and backtracking, and then how you exploit the CSP structure. So very quickly, I want to go over the assignment that's for this module. So I've opened up Homework 6 Queen. You can get this from the Get site, a link I provided, as well as the GitHub link I provided, as well as it's on the D2L website. But basically, this isn't as big of a program as the other ones. It's only one file. And it looks for the clashes. And so what you'll need to do is we have just this this state class, which you can pretty much keep it as it is. But what you need to modify is the Queen 8 OR class. and it has some basic goal checking and checking for clashes, but it has no backtracking. So for this assignment, you need to do backtracking and also do the min-const function. So you would add that you have to put var, you can check here, do some backtracking, as well as the state search, and modify those to have the additional parts. So this is a pretty, implementing the algorithms will be big, but this is going to be a pretty small program compared to the other ones. And when you run it, you can see the positions of all the other ones, and it's expanded the number of states. This is fairly quick. You notice the number of queens is 8. Say if I do this for 10. I've already ran it, and it took a while to get done. So notice how many, it's growing exponentially. And so if I went up to like 14 or something like this, that would take a very long time. So what you need to do is implement it in a way with backtracking and doing the local constraint testing. And then I got the information for this, for the acknowledgements here. The main thing I went over was the computer science 421 from University of Maryland College Park, and the class, as well as the AI instructors resource page from Berkeley. Hope you enjoyed this lecture, and until next time.